All right, some more applications of being continuous. So if I've got these two graphs, so C is a constant, here I've got a parabola, and here I've got a cubic graph. So in and of themselves, those two are continuous. But what I'm going to want to do is I'm going to want them to join together at 3 so that it is continuous on all reals. So parabolas are continuous by themselves, cubic things are continuous by themselves, but we want these two graphs to join together. What does the letter C have to be? So this is a necessary step. So I want you to write, I know that the limit has to go to 3 from the left-hand side, and I'm coming in on this function if I'm coming from the left-hand side, because this is x is less than 3, and I want to make it equal to the limit from the right-hand side, and I'm coming in on this function if I'm coming from the right-hand side, because that says x is bigger than 3. So this is a necessary step, and the next step, from here to the next step, I'm actually plugging in or evaluating at x equals 3. Because I know parabolas, I'm allowed to plug in. I'm trying to find out where this parabola lands on. Because I know cubics are continuous, I'm going to plug in x equals 3, so I get 27 plus 3c. So now it's my job to solve for c. So I'm going to subtract this over, so 9c minus 3c gives me 6c. I'm going to subtract this over, so I get 15. And so c is 15 over 6, or 5/2. So that's the value of c that makes this function continuous. All right, so the intermediate value theorem. So there are two, so what I'm going to do is I'm going to show you that if I have criteria set, then I get the conclusion. First off, so the first criteria is if I have this function that's continuous on this closed interval, and if I have the f of a and f of b are not equal to each other. So let me just get a little picture going. So here's an a, here's a b, and so here's starting at a and going up to a b here, right? They're not equal to each other, so f of a and f of b go to two different y values. Okay, so it's continuous, can draw it without lifting my pen. These two different y values are not the same. Then let n be a number between these two. Okay, so I'm just going to put n right there, in between somewhere. Then, as long as I have these two criteria, so this was the second criteria. So the second criteria was these are not equal and there's an n between them. Then there is a number c in between a and b, so that f of c is n. So think about that. Doesn't that mean there's a c here so that its y value is n? Yes. Okay, so how do we apply this? So this is one way it could come reworded towards you, and this is another way, so I try to be comfortable. I'll always tell you to use the intermediate value theorem to show there is an x such that the function equals 0 where this is the function. Or you could be asked to prove there is a root, and isn't a root where f of x equals 0, it is, for this function using the intermediate value theorem. Okay, so how do we do this? So first off, I need to pick a closed interval. I need to have an interval that I'm going to start and end at. So what I'd like to do is show that this function crosses the x-axis. So I want to pick, I'll just put letter A where the y value is negative, and I want to find a letter B where the y value is positive, right? So I'm going to start off with x equals 0, just because it's a nice easy number. So if I use x equals 0 in here or here, right, I get f of 0 is positive 1. Okay, so let me just get the picture going again. F of 0 is positive 1. So there we are. So now what I need is I need to pick some x value where the y value will be below the x-axis. So because I'm looking at that, I'm going to say, let's choose x equal negative 1. because I see lots of negatives in here, yes? So f of negative 1, let me go slow so I don't make any mistakes. I get negative 1 minus 4 plus 2 plus 1 plus 1. So this will give me 2, 3, 4 minus 4. So this gives me a negative 1. So when x is negative 1, the y value is negative 1. Okay, so I've done it. I've found a closed interval. So you have to do a little bit of, I would call this on the side here, scratch work, right? This isn't my proof. I have to use the intermediate value theorem. So kind of like squeeze theorem, you kind of have to write it up. Okay, so what I can say now is that this function is a polynomial, so it's always continuous. This function is continuous on negative 1 comma 0. So between here and here, it is continuous. So you have to go pick this interval, right? You have to go find, you have to discover that. Then I know that these two values are not the same, but the n that I'm looking at is 0, right? I want this n to be something in between. So n is 0, and I'm going to say it's between, and so I'm looking here, f of negative 1, which is equal to negative 1, and f of 0, which is equal to 1. Okay, let me stop there for a second. So what did I do? I said this y value of 0 is between these two y values, where the y value that goes with 0 is 1, and the y value that goes with negative 1 is negative 1. So what I have is negative 1, 0, 1, right? So I know I crossed over this y value of 0. Therefore, there is a value of c so that, in between negative 1 and 0, so that f of c equals 0. This 0 being this 0, right? I know there's some c in between negative 1 and 0, so f of c equals 0.